CobaltStrike is probably the tool in the center of the discussion surrounding commercially available and open source offensive security tooling that is abused for malicious purposes. In this talk, we are going to discuss some aspects of CobaltStrike detection, detection evasion, and Konstantin will also provide us with some insights into malware campaigns that we have observed delivering CobaltStrike payloads. The first part of the talk will provide a general introduction into what CobaltStrike is, why it is so well liked, and how the final CobaltStrike agent is actually loaded into memory. The second part will discuss a potential scenario where well-known malware such as CobaltStrike, or as I'm using for my demonstrations, Metasploit, is deployed against a modern Windows endpoint that is protected by common antivirus solutions. The purpose here is to demonstrate that malware, even if it is well known and signatures exist, can still be effectively deployed against many targets. The concluding part of this talk will highlight some malware campaigns that we have observed dropping CobaltStrike. Okay, let's talk about some CobaltStrike basics now to give you an idea what this framework can actually do. CobaltStrike was initially released in 2012 as a commercial successor to Armitage, a Java-based UI for Metasploit. The author of both tools is Raphael Matsch, a well-known hacker and entrepreneur in the security industry. He founded SpectreOps and 2017, an IT security service provider that is relatively well known. CobaltStrike was sold to Help Systems in 2020. CobaltStrike is very easy to set up and can be used by novices for basic operations. There are many available community profiles, plugins and tools that integrate into CobaltStrike that can be used with little prior knowledge. However, utilizing some of the more advanced features in complex scenarios and writing custom extensions and loaders is much more demanding. Red teamers generally like CobaltStrike for the flexibility, automation, customization, and extension features it provides. Unfortunately, criminals love it for exactly the same reasons too. The CobaltStrike framework is made up of several components. The CobaltStrike C2 server that is communicating with CobaltStrike beacons, which are the CobaltStrike agents, is referred to as Team Server. Operators can connect with the CobaltStrike client, a GUI tool that allows control of the server and the agents to the Team Server. The CobaltStrike beacon is written in C. It's about 300K small and lives in memory of the compromised systems. Beacons can communicate via several C2 protocols with the server, among others DNS and HTTPS. The command and control traffic is customizable via so-called malleable profiles. These profiles are often used to configure CobaltStrike in a way that the C2 traffic looks like traffic of a legitimate application or website. Of course, more creative use of that feature, for example for domain fronting, is also possible, as we will see later in this presentation. The files that contain the encoded beacon payload are also customizable with the artifact kit. Furthermore, the client-side capabilities can be extended with so-called beacon object files, or BOF. These are modules that are loaded by the beacon at runtime and that can provide additional functionality. There is a significant collection of open-source beacon object files available, for example implementing more stealthy credential dumping functionality or some exploits. CobaltStrike is also scriptable with aggressor scripts. These are scripts that can trigger actions based on callbacks or user prompts. And of course, there's also a quite large open source collections of these scripts available. Some examples for the use of aggressor scripts would be to integrate CobaltStrike in a chat solution to get notified of new shells or to automatically triage a system when a new beacon connects. Beacons can also connect to each other to form a peer-to-peer network, which is useful when operating in a properly segmented environment where the public internet may not be reachable from machines deep within the target network. In these cases, beacons and less restricted network segments can relay the command and control traffic to the C2 server. CobaltStrike also brings some infrastructure for credential management and lateral movement with the just collected credentials using a PSExec-like implementation. Also, there is a VMI-based lateral movement feature available. Now let's zoom in on the agent component. Like I already mentioned, the CobaltStrike agent is usually referred to as beacon. The format of the beacon is an injectable DLL that lives in memory and usually does not touch the disk in an unencoded state. Beacons contain all code necessary to speak various available C2 protocols, so it is possible to switch C2 protocols during operations. For example, a beacon may only use DNS for C2 communications when the target is not actively worked, and then switch over to HTTP for more bandwidth when the operator intends to perform actions on that endpoint. As I've mentioned before, beacons can load extension modules, either user-defined modules, but there are also some modules that are already available in vanilla CobaltStrike, such as a VNC module. The beacon DLL is static for a given build of CobaltStrike. Accordingly, signatures for process memory on the beacon itself are very reliable. I've also mentioned that the artifact kit is there and can be used to customize CobaltStrike droppers. The artifact kit is a collection of source code that can be used to build a template file, in which the encoded CobaltStrike payload is injected. Along with this beacon template, for exe files for example, CobaltStrike is provided with a small script that describes how the payload must be encoded. In the end, the payload is encoded with the provided script, and a buffer of many A's in the template file is replaced with the encoded payload. The artifact is a binary that you could potentially see on disk, while the beacon DLL itself will likely only be ever visible in memory. The default encoding for beacons in artifacts is a 32-bit key XOR cipher. After decoding the payload, it is made executable with virtual protect and then executed in a new thread. How exactly that create thread call starts the payload is something that I will come back to later. Notice, however, that the new thread simply starts executing at the beginning of the buffer containing the decoded beacon. And I've already mentioned that this beacon is a DLL, which you usually cannot just executing at the beginning. Let's go and find out how that is implemented in CobaltStrike. The hex dump on the top shows the first few bytes of a normal DLL, and the hex dump on the lower side the first few bytes of a decoded beacon payload, as it would be present in memory for the create thread call. You can still recognize the MZ magic at the beginning of the hex dump, which is a good indicator that this is still a PE file, but everything else looks a bit scrambled. Directly after the MZ, there's a bunch of data that looks like shellcode, but this program cannot be run in DOS mode string also is gone. What happened to that string is something that I will explain a bit later. The assembler code on the left side of the slide is a disassembly of the data at the beginning of the beacon file, starting with the MZ. Pop R10 corresponds in 64-bit x86 code to MZ when you compile it. In order to fix this, there's a push R10 instruction following the MZ or pop R10 instruction. Then there is some code to build a stack frame, followed by a load effective address instruction that loads the address of the start of the beacon buffer in memory. To this address, a fixed offset is added. The resulting address will point to a reflective loader implementation inside the beacon DLL. A reflective loader is a piece of code that implements some of the functionality that usually the operating system would take care of for you when you load an executable file from disk. This includes allocating memory for the different sections of the binary, processing imports and relocations. In essence, this code allows the beacon to initialize and later run an executable without having it written to disk first. The call rbx will then call the reflective loader code, and this code returns a pointer to DLL main, the entry point of a Windows DLL. This entry point is already called for the first time by the reflective loader, since that is required to initialize a few things in the C runtime. During this call into DLL main, the loader log is set, which prevents the creation of threads and the use of some synchronization routines. The shellcode proceeds to call DLL main a second time, this time with the for as a calling reason. This is relatively uncommon value for that argument. Usual values are 1 for DLL process attach or 2 for DLL thread attach, etc. For is the badly documented verifier load argument that you rarely see in normal code. The second call into DLL main then starts execution of the actual beacon payload. CobaltStrike beacons have an embedded 1-byte XOR encoded configuration that contains all the information required to connect to the correct C2 server with the correct protocol and specified customizations. The XOR key is in lowercase I or 0x69 for older CobaltStrike builds and a dot or 0x2e for newer builds. The hex dump on this slide shows a part of the decoded configuration. There are human-readable strings in there, but also some length and field type information that is binary encoded. The embedded configuration does not only contain information about the C2 protocol and channel, but also potentially a kill date that tasks the beacon to terminate at that configured date, and a PE file that is used to spawn new processes on the target. Some actions will task the beacon to start a new process and inject a payload into that process. The PE file specified in spawn to target is used for that. I think the default option for this setting is rundll32.exe. There's also a watermark embedded in this configuration that is a very simple 32-bit integer. This integer is supposed to be mappable to a given CobaltStrike license. However, since most threat actors use cracked versions, the watermark is often either completely missing or not that useful for the purpose of tracking individual threat groups. Konstantin will now talk about some CobaltStrike detection basics.
At first, I'd like to introduce you into the detection of malicious things in a sandbox environment from high-level perspective. So for malware analysis, you can use sandbox environments or bare metal, and typically one of both options are used to execute and detonate the malware. And then you can divide the detection possibilities into two sides. Into static detection, where you analyze and detect a given sample without running it, and into dynamic or behavioral detection, where you analyze a given sample while you run it. So examples for static detection are Jara rules, claim-AV rules, or other basic antivirus rules, and file metadata like bridge hash, the hash itself, the imp hash, file size, file name, or the file type. All of those artifacts can be used for static detection, of course. On the other hand, examples for dynamic detections are Sandbox signatures that match on the dynamic execution chain. For example, which Windows APIs have been called in a specific order, or Sigma rules, which do a bit the same actually, and of course network signatures like Snort or Suricata. The best detection is a combined approach of static and dynamic detection for malware analysis, but also of course for defending your network. If we now look into CobaltStrike detection and the specific detection possibilities of CobaltStrike, there are plenty, but none of them have been implemented by the CobaltStrike authors, of course. For example, you can detect CobaltStrike statically in memory by matching on the reflective loader or the injection stub code that Alexander just explained, or you can detect the beacon binary after the injection. You can also extract the configuration from the beacon out of the memory dump. When executing, there are also plenty of dynamic possibilities. For example, the network traffic inspection if a known malleable profile is used, or the name pipe if the default name pipe is used. And there is also a lot of possibilities for generic signatures like matching on process injection or process hololink techniques, just to name two of them, but there are of course, a lot of more generic signatures that can be used. It is important to note that a few detections only work if the default configuration of CobaltStrike is used. So if an actor uses, for example, a new malleable profile, there will be most likely no existing network signature for it. So every time actor changes the default configuration, it makes life harder for defenders to detect it. On the slide, you can see two screenshots of a sandbox run. On the left side, you can see that CobaltStrike OCs have been matched against the memory dump with a Jara rule for CobaltStrike detection. And on the right side, you can see that the same memory dump has been used to extract the CobaltStrike beacon configuration out of the memory dump. This configuration also only shows a few parameters. There are a lot more, but as you remember the slide from Alexander a few minutes ago, you can see that it's possible to extract the configuration out of memory again. Another cool way to detect CobaltStrike is the default name pipe. The default name pipe works pretty good, and most actors are too lazy to change it from the default value. Above, you can see a screenshot of a sandbox run that shows a Windows API call to anti-create named pipe file with the pipe name. And in the pipe name, you can see this MSSE-3107-server value. And this value is the default named pipe value. With the digits, of course, they change. And below, you can see a really simple Jara rule implementation to detect this kind of default name pipe. Moving on to network detection. On the slide, you can view an exemplary Suricata rule that detects the malleable C2 web bug profile of CobaltStrike when it tries to look like a Google web bug. And you can see that the signature is pretty easy to read. It looks for HTTP traffic coming from home net, so from internal traffic, going to external net to external traffic, and matching on the HTTP method HTTP GET. Additional, there has to be several URI parameters in the content match. So all of those UTM-CN, UTM-CS, UTM-SR strings have to be present in the URL of the request. And last but not least, you can see that the Google Analytics.com host is excluded from the match because we don't want to match on legit Google web bugs, of course. If you look into the configuration of the malleable web bug profile, you can see the same strings, and that is what I want to show you with this slide. You can find this on GitHub, and maybe you can now get a feeling about how easy it is for actors to change the default values, because you just have to adapt those strings in there, and then you will bypass the network signature that I've showed you before. So now we have demonstrated how to detect CobaltStrike in the network during delivery and installation in a sandbox environment. And Alexander will now give you more insight into how to detect CobaltStrike from the endpoint level.
The second block of the talk will cover some techniques that actors use to evade protections on a modern Windows endpoint in a way that allows the use of well-known tooling, such as CobaltStrike or Metasploit, for attacks, even though most vendors should have static signatures for the tools itself. I use Metasploit for my demonstrations, which is usually even better detected than CobaltStrike, but all these techniques would work for a beacon payload as well. In order to have a cohesive story that I can use to explain the different detection opportunities and evasion techniques, I use a fictitious scenario where an attacker attempts to compromise a Windows 10 endpoint with a well-known malware, in this case Metasploit. The goal of the attacker is to achieve persistence and retain access to the target system for a meaningful time. The first step the attacker must undertake is to get a malicious payload delivered to the target system. Two of the lines of defense that a typical endpoint has are smart screen filter and an antivirus software, such as Microsoft's Defender, that may scan the file. The smart screen filter check is triggered when the user attempts to run a downloaded program but completes before the program is actually run. I will explain Smart Screen first. Smart Screen checks downloaded files against the list of often observed files. If your file has not been seen by many other Windows endpoints, you will be presented with a message that you can find on the right side of the slide. Smart Screen only checks certain executable files. I'm not sure what the exact list of supported files is, but ISO files are apparently not on that list. Thus, you can deliver your malicious exe in an ISO container file that will completely bypass Smart Screen. I've prepared a short demonstration for that. Let's dive into this brief demonstration of Windows Smart Screen filter bypass by using ISO container files. I'm going to navigate the website that is serving an obviously malicious file in this case, so it's local privilege escalation that will add another admin account if it runs successfully. So let's see which users we currently have active here, and now let's download this file and select execute. So now we get this warning message from Smart Screen. In this case, it says, okay, the connection with a Smart Screen is currently not possible. This is since that this VM does not have public uplink, so it's like in a local lab network, and it's not able to actually connect to the outside. But we will see that if we download an ISO file instead, that's containing exactly the same file. It has even the same hash sum. It will execute without issues. So now let's check, and we see that there's another admin user added here, which has not been present in this first net user command. So this ran just fine without any issues and further warnings. The next hurdle is an antivirus scan. This diagram very roughly models what could be going on when a file is scanned, for example with Windows Defender, when a new file is downloaded or written to disk. In order to determine whether a file is malicious or not, most AVs use a combination of different techniques and technologies. Windows Defender, for example, has a nice emulation sandbox that tries to emulate execution of a binary in a very lightweight sandbox environment. Defender tries to assess what would happen when this file is executed by detonating it in this local sandbox. This also helps defeating quite a wide range of packers, since these may unpack their encrypted payload in the sandbox and allows Windows Defender to grab it. I will show you a small demonstration for the evasion of the Windows Defender sandbox next. Now let's take a look at the Windows Defender sandbox. We have a payload here that should be detected by Windows Defender. As it is now, it's not that important what it does. In the end, it's staging a metapreter that's connecting to this server here. And we got a relatively up-to-date Windows 10 VM here, so signatures are from, I think, 3 days ago. Now, let's compile our payload without the evasion enabled. This should give us an executable here. I will copy this now into the target system. And now Windows Defender should already scan it. Let's wait a few seconds. And then we should get a notification. There it is. So, thread was found. It even detected metapreter. So let's go and remove that. It takes a bit. Now it's removed. Okay. So now let's look into possible evasions. The sandbox evasion I've implemented here plays of the limitations that are possible in an emulated system, basically. There are also other sandbox evasions that work against Defender as well as against classical sandboxes, some timing-based things, but this is a very simple and reliable evasion against Defender. What's going on here is that we have a function pointer that's pointing to very likely non-executable or not even allocated memory in the virtual address space. So this will deterministically segfault and go into this exception handler and then continue execution. Now, if the emulation either simply skips this call or is not able to properly handle this exception, then we are ending up in the terminate process statement here, which will, of course, shut down the process, and Windows Defender will think, okay, the program got terminated. Apparently nothing malicious happened here. So let's check if this proves to be correct. And let's recompile this. Now we got this freshly compiled dropper here, and I'm dropping it here. Yes, to actually show you that Defender is scanning this, I'm also manually scanning it. And nothing happens. So now let's execute everything. And here it is. We got a working Metasploit shell. Most antivirus systems have some type of static detection for on-access scans implemented. This is not necessarily a flat scan of a file. This can include unwrapping of container formats and recursive scanning of nested files. But either way, I will not bore you with a demonstration of that type of evasion, but I will show you a small code snippet instead. Evasion of malware detection with static signatures for files that reside on disk. We're not talking about static signatures matching process memory just yet. It's often very easy. One common approach is to embed the payload in an encrypted form and then decrypt it during execution. This type of evasion can be defeated with sandbox emulation systems, such as the Defender sandbox, at least if these are not otherwise defeated. This is an implementation of a small dropper in C that decodes an RC4 encrypted payload, makes the memory containing the payload executable, and then starts it. RC4 is a relatively simple symmetric stream cipher that is well suited for this type of obfuscation, since the algorithm is very simple to implement and does not require any static S boxes or other cryptographic constants that could give away that there is actually RC4 implemented in this binary. The final part of this antivirus on access scan that we want to consider here is the processing of meta-information. Most antivirus solutions consider some type of meta-information, in this example, whether the binary was signed by a trusted entity with authenticode. A common technique for malware is to use legitimate signed applications that are vulnerable to DLL sideloading to use this application to start the malicious payload. Certain groups are notorious for abusing the Google Chrome installer to sideload a malicious DLL, for example. Another possibility is to acquire a code signing certificate to directly sign the malware. This happens surprisingly often, but I don't have a code signing certificate to burn for this conference, so I'm going to show you a DLL sideloading demonstration instead. For the DLL sideloading demonstration, I have prepared two binaries. One is the kndbwm.exe and one is the stripped version of the same binary. So this one here is signed by Rivet Networks LLC and by Microsoft. So this is some kind of networking tool or for Wi-Fi stuff, which is not really relevant here, but what is relevant is that it imports this pdh.dll without a safe path. So if you drop that DLL in the same directory, it will simply import that DLL and will execute the DLL entry point and actually a few exported functions. This is the stripped version, so that's the same binary as this one, but I have removed the signature using sign tools. So you see there's no signature tab here. And the payload here is again our Metasploit payload that should connect to the server here on the left-hand side. I'm going to start by executing the actual stripped version of the binary. and you see some activity. So it opens a window and it writes a file. So it's probably not a good side-loading binary for actual red teaming or actual attacks. And now Windows Defender detected Metasploit and killed the process. So it detected Metapreter and asks, okay, what should we do? Let's say remove. And now it should, in theory, yes, remove the exe file. So of course, Windows Defender does not know that the payload is actually in this malicious DLL. And now it's removing the, in fact, rather benign original binary, just without the signature. So to clean up a little bit, I'm going to kill these now defined sessions. And now I'm going to start the signed version of this binary after the session cleanup is through. And we get basically the same picture here. So some activity here and probably some writes to this file. There's another one. And now we got our session. Let's connect to the session and do something to show it's alive. Okay. Now Windows Defender didn't really complain until now. Let's go and force a scan. So this quick scan will also do an in-memory scan of running processes. And there's nothing. Windows Defender is quite happy. This is the old event, I think. Yeah, that's a stripped event. And this was the memory detection. So this is still active. And we got our absolutely unmodified vanilla Metapreter shell on an up-to-date Windows 10 endpoint. Now that the payload got safely delivered to the target system and is starting to execute, the dynamic detection of the endpoint protection system may kick in. The actual implementation of dynamic detection in different products can be quite complex, and I'm using a specific detection event to discuss an evasion feature that's implemented in CobaltStrike here. For this, I'm looking at the point in the execution flow when the decrypted or decoded payload is just about to be executed in a new thread. AVs tend to scan the memory that is going to be executed in new threads under certain conditions. This can catch payloads that are obfuscated with techniques like the RC4 encryption that I've shown you just before. One technique implemented in CobaltStrike to defeat this is targeting the acquisition phase by trying to prevent the AV software from acquiring and scanning the correct memory, which would be the decoded payload in this case. The C code on the right side shows a reimplementation of how the CobaltStrike beacon payload is started after it got decoded by the artifact. This is the same code that we have seen before. The interesting part of this code is the create thread call at the bottom. The third argument, here pointed at a trampoline, specifies the memory that should be executed in the new thread. In this case, the memory that is containing the code that is intended to be actually executed, the actual beacon payload by the new thread, is pointed to by mem and provided as a fourth argument to create thread, instead of being provided directly as the entry point for the new thread. Create thread will pass the fourth argument, here mem, to the trampoline function as first argument. The trampoline function is only a call RCX, and RCX is in Windows x64 standard calling convention the first argument. And this is mem here, so execution will be going from the call RCX trampoline to the malware code. An antivirus solution may see the call to create thread and inspect the memory of the thread entry point, which would be the trampoline function or call RCX, and not the actually decrypted malware code. CobaltStrike, since version 4.2, has a new feature to evade the static scan, in the case that the antivirus solution manages to actually acquire the correct memory that holds the decoded beacon payload. Let's take a look at that. This relatively new feature encodes part of the beacon DLL that resides in the part of the memory that is just about to be executed by the new thread with a 1-byte XOR cipher. The decoding step is implemented in the reflective loader code itself. This has the added benefit of hiding the reflective loader code in memory when the beacon is fully staged, which is unfortunate from a defender's perspective, since generic signatures on reflective loader code tend to be very effective against CobaltStrike, but also against other tools. I've drawn up this visual help to make you better understand what's going on. This depiction shows the state of the beacon when it has been decoded by the artifact implementation and is just about to be executed in a new thread. The small shellcode stub at the beginning is not encoded and execution starts there. Then the reflective loader code is called, which resides in the text section of the DLL file. That is at this point just written somewhere to memory. The reflective loader code then proceeds to copy section data to memory and decodes parts of the sections where required. This will conveniently encode the reflective loader code in the loaded text section, as I've mentioned before. You can then basically invert the decoded and encoded parts of the text section. The text section is not the only part of the PE file that is encoded. For example, the import descriptors are located in the RData section, and these are also initially encrypted and are decrypted during the reflective loader phase. The remainder of the RData section is, for the most part, in clear text. You may remember the slide with the hex dumps from the first few bytes of a beacon DLL and a normal DLL, where the DOS string also got encoded. This also happened due to this feature. Then there is also some additional small tricks implemented that make it harder for antivirus systems to detect reflective loading. For example, the PE magic that sits usually after the MZ magic in the PE header is replaced by an NE, which corresponds to a 16-bit executable file, which is clearly not the case here. Most malware wants to achieve persistence on the target system at some point. One of the easiest way of doing so is to place a link or executable file in the Autostart directory directly. It is reasonable to expect that most antivirus solutions should have some kind of dynamic detection that at least flags such behavior as potentially malicious. In addition, there will probably be another antivirus scan of the drop file, but I've already discussed that in the delivery phase, so I'm going to skip it here. Next, I'm going to show you how to evade the generic behavioral detection of Autostart persistence on a Windows 10 endpoint running Kaspersky. The core concept for this evasion is to blend in with normal activity patterns that you would expect to see on an endpoint from a given process. In case of the Autostart persistence, I'm going to drop the file to Autostart from the context of the explorer.exe process. This looks similar to the AV as if a user would use the Windows Explorer to simply drop a file there. Now let's take a look at how we can achieve persistence in a Windows 10 host that's protected by Kaspersky Internet Security. So I have to show you a little bit C code so that you properly understand what's going on. This dropper is trying to directly achieve persistence by copying itself to the Autostart directory. It's doing that by retrieving the path to the current file, so the exe file that's actually currently executed, and then it's concatenating the app data environment variable that points to the app data roaming directory with the remaining path to get into the startup directory. Then it will generate a random file name and write itself to that location. The payload here is not Metasploit in this case, but rather an in-house C2 agent, simply because Kaspersky would directly detect and kill Metasploit as it's proper. So I will build this dropper here now. That's the new build. and copy it over into this VM and execute it. And it got directly killed. So this process was terminated. Let's see if something more happens. And the binary got removed. This is how it should be. Now let's see why this happened. So there was a match on PDM, Trojan, Win32, generic. This is likely, at least in parts, due to writing itself to the Autostart directory that could be very well considered malicious behavior. So I will restore the initial state again from a snapshot, and I will add a little bit code to the dropper to actually not automatically persist on hosts that are running Kaspersky. So let's build that. And it got built. So now I'm going to copy that new build over to the VM. And before I execute that, I'm going to load a small script in my C2 server. So this is just a very small automation to basically do a similar thing than what we have seen in the C code or C++ code. So this tool is retrieving the app data environment variable and then concatenating it with the remaining required string to actually end up in the startup directory, and then write a file that's named zoom.exe there with the content of the local dropper.exe file. Now let's execute the dropper. And we do see a connection. If I'm quick enough. It was too slow. Okay, but it was just written here, so we actually got our persistence here. After successfully persisting on the target, the next goal is to have active command and control for a meaningful time. It does not really help an attacker to have access to a target system for only about 5 seconds after boot and the antivirus system kills some newly spawned process again. There is a risk of being flagged by a dynamic detection mechanism as well as getting caught by a background in-memory scan. Some endpoint protection products also bring network traffic inspection capabilities, and some corporate network setups have external network traffic inspection solutions. For the dynamic detection case, there are ways to attack memory acquisition in some products, but I want to show here that this is not always necessary. In the demonstration that I've prepared, I'm going to attack the remediation phase, the step that would ordinarily remove the malware from the system. The malware will still be detected and an alert will be issued, but without user interaction, some antivirus products do not touch system processes to remove malware automatically. This means that if I can inject malware into, for example, the explorer.exe process, it will not be automatically shut down and removed even when it is detected. I will use a similar setup for this demonstration as we've seen for the last one. So on the left side, there's a C2 server running a custom C2 tool, and then there is a Metasploit shell 2. So the plan is to get the agent that corresponds to this custom C2 tool running on the target undetected, and then stage Metasploit as kind of a placeholder for CobaltStrike in a later stage. That's very similar to what we see with some crime actors that have a little bit smaller loader tools or staging tools that actually have some functionality to do, for example, host fingerprinting, or maybe even execute arbitrary commands on the host, but that can also load further malware later on. And these little bit smaller loader tools are often built to heavily evade and being heavily obfuscated, so that AV vendors find it hard to keep up to date with signatures if stuff changes frequently. And that's much more easier done with like a smaller tool where you can easily customize stuff than if you would have something like a CobaltStrike, or for that matter also Metasploit. That's a little bit harder to completely rework so that it's not detectable in memory anymore after it's running. On the right side we have again Windows 10 VM running Kaspersky Internet Security. I'm going to build my dropper now. And copy it to the target system. And if everything goes well, I should get a shell here without triggering any detection. So that worked. And now I will use this shell to load a Metapredator shellcode. So this will stage basically a Metasploit. So we will see a shell here after this loads, and Kaspersky should be able to pick up on that. So there are signatures for this. So this shell is live, it's working, and now I will just let it sit there for a while and come back later to see what happened if Kaspersky detected it, and more interestingly, if this was actually indicated to the user and remediated. After waiting for a while, let's check back. So apparently Kaspersky complains that definitions are not up to date, and it's still stuck. So that's probably an issue with the VM, I don't know, but the beacon is still alive, even though this got detected. So we see that a signature matching on reflective loader matched on memory. Probably couldn't attribute that to a file, but nonetheless it got detected, but you would have to manually remediate to get rid of that. I have briefly mentioned malleable profiles that can be used to configure the C2 traffic to emulate benign websites and applications. These can be used to configure CobaltStrike beacons for domain fronting too. The example shown here is a beacon configuration that we have seen in actual production data. I have redacted the Azure endpoint since I cannot be sure that this was not a penetration test. The beacon was configured to connect to download Visual Studio Microsoft COM, which is a legitimate Microsoft-owned domain with the corresponding TLS certificate. This domain is served by the Azure Content Delivery Network, and accordingly, download Visual Studio Microsoft COM points through a CNAME to a subdomain of azureedge.net. When an HTTP request hits the Azure CDN, Azure will look up the CDN endpoint that is specified in the host header. Here it is redacted azureedge.net. This endpoint is registered by our CobaltStrike operator and configured to disable caching. The CDN will check its database and look up where the redacted endpoint is served from. This is the CobaltStrike C2 server, and Azure will relay the HTTP request to this C2 server. Azure functions essentially as the reverse proxy for the CobaltStrike C2 server at this point. The CobaltStrike server will then respond to the HTTP request, and the response is again relayed through Azure. This type of domain fronting is relatively hard to spot on the client side. The traffic is TLS encrypted, and download Visual Studio Microsoft.com is authenticated with a proper and valid certificate, so it's not easy to spot that there's anything weird going on here. Next, Konstantin will show us a little bit data on some campaigns that we have observed dropping CobaltStrike.
In the following chapter, I'd like to show you some recent campaigns and actors that use CobaltStrike and some general high-level metrics about CobaltStrike. We will start with a graph taken from Google Trends service, where you can look up the popularity of a search term in Google's search engine. The x-axis shows the time, the y-axis shows the popularity relatively baseline to the timestamp of the most popularity. So this means that a value of 100 as of today means that there has never been a time where the search term CobaltStrike was more popular, compared to 2018, where the term was only half popular than it is now. You can also clearly see that the term CobaltStrike started trending after its release in 2012 and was not a trend before that. So this chart can be seen as a global metric. The next chart shows you the number of email messages associated with the CobaltStrike payload in Proofpoint's email data observed over time. The x-axis shows the time again. The y-axis is linear and shows the number of email messages, but we can't share absolute numbers. But we can say that threat actors' usage of CobaltStrike increased by 161% from 2019 to 2020, and the general trend is increasing in the last years, as you can see. I have to note that the 21 figures include data through May 21, so I hope you can imagine the value being 4 times higher by the end of the year. This slide can be seen as a significant metric, but not as a global metric, of course, because it does not include the whole world. It only includes Proofpoint customers, and it only includes email traffic. Further, I have to note, we do not have insight in data from incident response cases where CobaltStrike has been dropped at a later stage. Maybe we did see more CobaltStrike, but we did not see it in the email execution flow because it was dropped at a later stage, and then it doesn't count as CobaltStrike from our perspective. CobaltStrike is currently used more and more by cybercrime and general commodity malware operators than APT and espionage threat actors, which have been using CobaltStrike a lot in the past. That's why we can see a shift from low volume targeted APT campaigns to high volume widespread cybercrime campaigns. And the chart on this slide shows you the number of customers targeted by CobaltStrike over time, where the x-axis shows you thousands of customers and the y-axis the time again. Again, you can see a clear trend towards more customers being targeted. And of course, the 21 data is again only through May. Another interesting thing to do is to map important publicly reported attacks that used CobaltStrike on a timeline. From 2016 until early 2018, you will most likely find targeted attacks from APT actors. But starting in 2019, the public reported articles about CobaltStrike threats that used this kind of red teaming tool are immense and also include a lot of large-scale cybercrime actors. So this also represents the trend I've tried to show you previously, that there is a shift from APT to cybercrime and a shift from low volume to high volume. You will find the articles behind the events linked in the slides. And I like to point out the huge SolarWinds supply chain attack in December 2020, where multiple government and security companies have been infected with CobaltStrike. And in this case, it was delivered via compromised SolarWinds software and then dropped at a later stage. The latest huge threat happened in May 21, where the Nobelium actor, which is most likely APT29, a Russian attributed threat actor, used CobaltStrike, dropped from an ISO file and a loader in a later stage. The trend of more CobaltStrike usage can also be explained that more and more CobaltStrike versions are getting leaked publicly, and it is very easy to download a cracked version from the internet of CobaltStrike. I've just looked it up today, and the latest version is from May 21. So yeah, you not only get outdated CobaltStrike versions in the internet, you always get the newest version. If we now look at a few campaigns, we will start with an APT actor, which is called TA415 or Barium or APT41. And it used URLs leading to CobaltStrike as a first stage payload during mid-2020. So an email with a link leading to Google Drive, and you downloaded the CobaltStrike exe from Google Drive, and then you got infected with CobaltStrike. The same actor continued using CobaltStrike in 21 against the airline entities. You most likely have heard about the big airline heist. I've linked you the article for that. So this is a classic CobaltStrike usage from an APT actor. Another actor, which is a large cybercrime actor called TA575, and it delivered CobaltStrike in June 21. There was an email with a OneDrive link leading to an Excel document with a macro, and of course, also in 21, macros are still getting enabled and clicked on. The interesting fact for this attack chain was that it was variable and very complex, as you can see with the multiple stages. And they started on June 21st with an email leading to a URL leading to an VBA macro inside an Excel document, dropping CobaltStrike. 2 days later, they changed their attack chain, and instead of dropping CobaltStrike directly from the macro, they used 2 intermediate PowerShell stages that later downloaded CobaltStrike, and which increases, of course, the difficulty for antivirus vendors to detect it and to follow the whole execution chain. And also, of course, payloads can be switched dynamically, and every victim can have a unique payload, a unique CobaltStrike configuration, and a unique CobaltStrike payload delivered. So this is a really cool example for CobaltStrike delivered in the first stage. But of course, we also see in the email execution flow CobaltStrike being delivered as a second stage payload, for example, by TA547, which delivered CobaltStrike with an email attachment, which was an Excel document with a macro again, which dropped TrickBot, which then loaded CobaltStrike as a secondary payload, because CobaltStrike is a pretty cool tool to use for C2 communication, and it's way more flexible than TrickBot is. So that's a little bit of insight from our email data. Of course, as I've mentioned before, CobaltStrike can also be dropped at later stages in an attack chain, but then we don't see it anymore, because sometimes the actor gets the initial infection and then drops CobaltStrike manually. And of course, you don't see such things in the Sandbox run because it's just too short.
Okay, thank you very much for following this presentation. Since there are right now no questions, I would directly follow up with a small basically bonus demonstration that is demonstrating this evasion chain that I've used to model some of the CobaltStrike evasions, but also some of the evasions that we generally see in other first-stage malware to evade a bunch of other antivirus systems, so that the impression is not that there are like few select systems that can be evaded specifically this way, but rather that this type of methodical engineering of evasion and of antivirus bypass works for basically every product. It's not tied to a specific product, and yeah, it's unlikely that there's anything out there that cannot be evaded in a targeted way. So let's see if this time the sharing of this video goes better. And if you got questions, feel free to drop them in the Q&A tool.
I have a final demonstration for you chaining all these evasions that I've shown before in the second chapter together to evade a bunch of antivirus systems. So the idea here is to show you that the systematic approach of antivirus evasion is not restricted to specific products, or that there's any product that's especially vulnerable to that. With enough effort, you can probably evade most, if not all, products in a similar fashion. So initially there is the Defender Sandbox evasion, which is tailored to Windows Defender, of course. Then there is the Autostart, so I left that in case it is no Kaspersky, because I already know Kaspersky will going to condemn this sample if it tries to write itself to Autostart. And then there's payload decryption and payload injection into explorer.exe using direct system calls. So I have to know that it's possible that some of these AVs would perform maybe a little bit better detecting this injection, since some antivirus solutions have actually a way to monitor direct system calls using some hypervisor stuff that turns out to be a little bit unreliable in nested virtualization setups. But I'm very sure that there are ways to evade this on bare metal too, just to have that said. Then there is the payload that's actually injected. So similar to a CobaltStrike payload, this is an injectable DLL. It's basically the exact same technique. So it's a DLL where I write a small shellcode stub at the beginning. That happens somewhere here. That looks very similar to what's going on with CobaltStrike. So there's also an offset calculated to the reflective loader function, which is then called, and then there's a second call to the DLL entry point. Now the actual payload is implemented here, and it's basically the same as with the injector itself. So it RC4 decrypts another shellcode again, which is in this specific demonstration an injectable version of the C2 agent for our in-house C2 tool. This is then made executable and invoked. So let's build this thing and start with Norton. On the C2 server side, I have again my custom C2 tool and then a Metasploit set up with a staged reverse HTTPS handler and a reversed unstaged HTTP handler. So I'm doing it this way because Norton has a pretty decent network-based detection and will detect staging of something that looks like DLL, injectable DLL or injectable shellcode. So this would be detected by Norton. So I'm going for this other payload for this specific host. This will stage, hopefully, Metasploit. That looks good. and everything seems to be working and active. And I'm directly going to continue with the second host. This is a McAfee protected system. There's the agent. And here I'm again using the staged HTTPS metadata payload. This is also active. The next target is the Kaspersky host. And I'm going with the staged HTTPS metadata here too. And this is also active. And now let's look at the last target system, the Defender protected system. And this small waiting time that we have here is again caused by the initial on-axis scan. Probably the most time is taken by the Sandbox simulation. And again, there is a shell. So we got all shells running, all shells are active, and there's no alert on any of these systems. So endpoint protection is happy. And we are good. So maybe a final note. The techniques I've shown here are relatively common, so there's nothing very special here. The combination, of course, requires a bit of research, but the overall effort of implementing something like that is more in the ballpark of one afternoon versus maybe a few months to build a proper C2 tool that's capable of implementing lateral movement, scriptability, etc. So also most of these antivirus solutions will, if you let everything sit for at least 24 hours or longer at some point, pick up on the Metasploit payload in memory due to scheduled background in memory scans. And I personally think that it's really worth checking the configuration of your used antivirus system to make sure that these scans really happen and happen maybe a little bit more frequent than every 24 hours, which is the default, for example, for Windows Defender. Also, something that unfortunately happens not that seldomly is that enterprises log their antivirus alerts to some kind of CM or log, but don't really look at them. So I've initially shown that, for example, with Kaspersky, there may be an active implant that got alerted and that's still active, but that didn't got remediated due to a lack of user interaction, or with enterprise deployment, it's also depending on the configuration, what's done automatically and what needs to be prompted. And people tend to miss these alerts and not react. So don't assume that if you get an alert for an antivirus scan from your EDR or AV solution that this thing is gone. You have to investigate and see what specific type of threat that was and whether there's further action required to remediate this. Host-based antivirus and protection solutions are a very important part of overall security, but they're not almighty and there are always holes to slip through as an attacker.